I'm happy to introduce our next speaker, Jagna Wiśniewska, who will talk about periodic orbits on tentacular hyperboloids.
Yes. Thank you. Thank you for giving me the opportunity to speak here. I hope you hear me well. Today, I would like to acquaint you with the topic of my research. We were going to talk about dynamical systems and periodic orbits of Hamiltonian flows on certain energy hypersurfaces, more precisely on tentacular hyperboloids. So let us start with a quick recap. So we will be on the same page with the basics of Hamiltonian dynamics. We have a symplectic manifold, and then to each function of the symplectic manifold, we can associate a certain vector field called Hamiltonian vector field. It is uniquely defined through this equation here. And we would like to analyze those. So the first observation we can make is that the Hamiltonian vector field preserves the Hamiltonian function itself. So in our analysis, we can actually restrict ourselves to a level set of the Hamiltonian function and look how the Hamiltonian flow behaves on this certain energy level. So let's maybe also think why the Hamiltonian dynamics is interesting at all. Hamiltonian dynamics arose from classical mechanics, which was to describe classical physical systems. So examples of those are to be found in celestial mechanics, where we have a couple of bodies which interact with each other through gravitational forces. And a real life question would be, okay, so we have those, and now we want to put a satellite somewhere in between, and where to put it so it would not fly away to infinity and that it would not crash into one of the planets. So it is, in fact, a Hamiltonian system, and we know that the energy is constant on the solution. But in this case, the energy level sets might be non-compact. Well, the non-compactness comes from two things. One, the crashing into the planets, and the flying away to the infinity. So this is actually that's the motivation to go into the non-compact energy hypersurface realm and try to understand close orbits on a given non-compact energy level set. And the more mathematical question would be can we actually relate the question of existence of the periodic orbits to the geometry of the energy hypersurface itself, how it lies in the phase space? Okay, so having that in the back of our minds, we go back to math itself. So our setting is, we have a symplectic manifold, which is exact, so it has a global primitive and satisfies some convexity conditions at the infinity. We have a hypersurface in this manifold, and we require the hypersurface to be of exact contact type. So the primitive restricted, there exists a primitive of the symplectic form, which restricted to the tangent bundle of the hypersurface is actually a contact form. So it satisfies this contact type condition. And then we choose a Hamiltonian on our symplectic manifold such that this hypersurface is going to be a regular zero level set of this Hamiltonian. So in the setting, we can define a flowing object, the Rabinovitz action functional. So it acts on the loop space times r, the real numbers, and to each loop and number, it associates another number. More precisely, the integral of the primitive over the loop, and then the integral of the Hamiltonian over the loop. And then this additional ether parameter pops up. If it was not for it, if it was not actually here, then some of you probably would recognize the action functional from the Floer theory. But this one has this additional parameter here, which acts as a Lagrange multiplier. So as we will see, it's going to pick up all the periodic orbits on this given hypersurface sigma. So the critical set of this Rabinowitz action functional consists of a solution to this reparametrized Hamilton's equation. So we have this ether parameter here, and we have that our loops have to lie on the hypersurface sigma. So every non-degenerate periodic orbit is going to appear in the critical set. Actually, not. It's going to appear in S1 times Z family, because the S1 comes from the S1 action on the loop space, which leaves the Rabinowitz action functional invariant, and the Z action comes from the Z action on the ether parameter, which corresponds to the fact we can go faster and faster, somehow wrap up the same loop several times. So, and we can go also the other direction. So that's why we have all the loops appearing more than once, in S1 times Z families. But apart from the non-degenerate periodic orbits, which are going to have the represented here, we have also the whole hypersurface sigma appearing. Yes, because if we take eta to be 0, and we take some point on sigma to be a constant loop, then it solves this equation, and this, of course, too. So that means that the critical set itself is going to have a component, which in case we take sigma to be non-compact, the component is going to be non-compact itself. For those of you who are familiar with the Floer theory, you can already spot the differences between the original Floer setting, because we have our critical points non-isolated, but appearing rather in families of manifolds. But so that's the first difference to observe. So what's the idea? The idea is to build a Floer type homology for this Rabinowitz action functional. And how do we do that? Well, we try to mimic what we know from the Floer theory, meaning we start with Floer trajectories as building blocks. What are those? Well, they are solutions to a gradient-like equation, with the Rabinowitz action functional. There are, in fact, some kind of embedded cylinders in this symplectic manifold time R. If we look closely, like if we look at the loop times the ether parameter equations, then the equations look like this. So on the right hand side, we have here appearing the two parameter family of almost complex structures, which we use to put a metric on the loop space. And then we have the pods which are look a little bit like the Hamilton's equations with the ether parameter. But for the differential equation which is governing eta, we have here the integral of the Hamiltonian over the whole loop. That means that this equation is not really localized around the cylinder, because it depends on the whole loop, which of course is another fun challenge. Okay, so once we actually understand Floer trajectories, we can try to build the complex. But as we are actually not having isolated critical points, we need to introduce another Morse function on the critical set. So we choose an arbitrary Morse function on the critical set, and then we we define the complex of our homology to be given by the critical points of F. And for simplicity, we just count them in Z2. And how do we define the boundary operator? Well, by counting so-called cascades. What are those? Well, it's easier to show than to write a mathematical formula. So if we are given two critical points of the Morse function f, p and q, a cascade between p and q would be a sequence of flow lines of the gradient flow of the f function, and then sequences of the flow trajectories connected with the gradient of the action functional. And we take one after the other, jumping from one connected component to the other until we hit the other critical point. And that would be a cascade between P and Q. These are actually quite nice objects, and they form moduli spaces, which allow us to actually define the boundary operator. And this boundary operator, due to nice breaking and gluing properties, is gonna square to 0, as we would like in a nice homology theory. So that allows us to define the Rabinowitz-Floer homology, which was first done in 2009 by Silleback and Frauenfelder. And they defined the Rabinowitz-Floer homology for compact hypersurfaces. And what were the properties? So, of course, the first, properties was that it is invariant of our choices of the almost complex structure and of the Morse function that was chosen for the construction. But the other interesting property is that it's actually invariant under compact perturbations. In which way? Well, if we have a smooth family of contact type hypersurfaces, which are compact perturbations of our a chosen sigma, then the Rabinowitz-Floer homology of those perturbations is going to be just constant, equal to the one of the hypersurface we started with. So we have some kind of a local invariance and constant on connected components of this hypersurfaces set, which is a nice property. The other property is very easy to spot. So if you recall the picture of the critical set, well, if we have no periodic orbits at all, then the only component of the critical set is going to be the hypersurface itself. And the cascades are going to be just the gradient flow lines on this hypersurface. That means that our Rabinowitz-Floer homology in that case is going to be equal to the singular homology of sigma with a shift, which is due to some kind of shift in grading. So that's a very important observation if we are actually trying to answer the question of the existence of periodic orbits. Those two together make a powerful tandem, meaning that, well, if we know that one, for a fixed hypersurface, we know that those the Rabinowitz-Floer homology of sigma is not equal to the singular homology with a shift. Then we know that there exist periodic orbits, and also there have to exist periodic orbits on all the contact type compact perturbations of this hypersurface. So this is the property that interests us at most. Third property is connected with a notion of displaceability. What does it mean if sigma is displaceable? That means that there exists the Hamiltonian diffeomorphism of sigma, such that the image of sigma under this Hamiltonian diffeomorphism is disjoint from the sigma itself. So that's what it means to be displaceable. And in case sigma is displaceable, then then the Rabinowitz-Floer homology vanishes identically is equal 0. So of course, this way they reprove the result somehow of existence of periodic orbits on hypersurfaces which are displaceable, combining the 2 and 3 property. But we were gonna concentrate on 1 and 2. And our question is, okay, that's a really cool tool. Can we actually generalize it to the non-compact hypersurfaces which appear in many of the classical systems and physical systems? And the answer is yes. Yes, at least some examples exist. And here the tentacular hyperboloids come into the picture. So what are those? Let's start with the simplest setting, simplest symplectic manifold we can think of, meaning the, R2n with standard symplectic form. And let's pick a non-degenerate symmetric 2n by 2n matrix. We require this matrix to be actually a block matrix. So through a symplectic splitting, it splits into 2 matrices. The first A0 is going to be 2k by 2k matrix, and we require it to be positive definite. The second one is an A1 matrix, which is 2n minus k to n minus k matrix. And we require it to have this property that the multiplication of A1 with the standard complex structure is hyperbolic. That means that all the eigenvalues of this matrix have non-zero real part. Okay. And then we defined, and then we can observe that the signature of A has to be n plus k, n minus k, because this one has, equal number of positive and negative eigenvalues. Okay, and with this matrix A, we define a Hamiltonian just by multiplying it. Here we already see how it looks in the splitting. We define a quadratic Hamiltonian, and we take, we want it to be non-degenerate in the 0 level set. So we have this -1 popping up here. And then we take the 0 level set. So the hypersurface, our sigma hypersurface is going to be the 0 level set of this Hamiltonian. And because the signature was 2n plus k, n minus k, that means that the sigma hypersurface is going to be a hyperboloid with a sphere n plus k minus 1 in the equator, and with n minus k somehow non-compact directions. So, and which of those are actually tentacular? So now having such a sigma in mind, it is tentacular if it's a regular set of a Hamiltonian as here above, with additional conditions on the eigenvalues and the Jordan decomposition of this matrix, JA1. So the A1 times the standard complex structure. We want the certain relations to be satisfied between the eigenvalues and the dimensions of the corresponding blocks in the decompositions, which are listed here. So having them satisfy that, we have a class of tentacular hyperboloids, and it turns out that for those hyperboloids we can actually define the Rabinowitz-Floer homology, which was the theorem that was in my thesis. And we worked on it together with Federica Pasquotto and Rob van der Forst. So it is not only well defined for those quadratic Hamiltonians, but also for any compact contact type perturbation of a tentacular hyperboloid. So if we take something if we take something which differs in a compact set, form a tentacular hyperboloid, but outside of a compact set, it is going to coincide with a tentacular hyperboloid, then for this object, we can also define this Rabinowitz-Floer homology, this invariant, as long as it is of contact type, of course, the hypersurface. And this object, so this extension of Rabinowitz-Floer homology does satisfy the properties that we actually wanted it to satisfy. So it is invariant under compact contact type perturbations, and it is equal to the shifted singular homology whenever sigma has no periodic orbits. So these are the most important properties that we were actually looking for, and it does satisfy them. So that's great, we are happy. But now the question is, okay, we have those relations, but can we actually compute the Rabinowitz-Floer homology itself? Like, that's a totally different question, which I was actually asked quite a lot after publishing that. But the good thing is, yes, we can. So in our recent paper with Alexander Falk and Will Murray, we were able to calculate the full Rabinowitz-Floer homology for the whole class of tentacular hyperboloids that I defined before. And it turns out that, well, even though at the first glance it does have two generators, but those appear in different in different places than the one coming from the shifted singular homology. So in fact, the Rabinowitz-Floer homology of those is not equal to the singular homology of the sigma of the tentacular hyperboloid, and it's obviously also not zero. Well, that's great. So we know there are periodic orbits, and someone would say, okay, well, but your Hamiltonians are super easy. Like, I can calculate the periodic orbits by hand. It's not the challenge. Well, yes, answering the existence for those, it's kind of obvious. But if we now combine it with the other property of the Rabinowitz-Floer homology, meaning the invariance under compact contact type perturbations, we get the existence for all the perturbations of this tentacular hyperboloids. And this is something one cannot so easily calculate by hand. So we are able to answer so-called Weinstein conjecture in this case, that if we have a family, a one-parameter family of compact contact type perturbations of a tentacular hyperboloid, then each of these hypersurfaces has to have periodic orbit. So
Jagna, you have about 3 minutes.
Yeah, I know, but I'm like, in principle, this is we arrive at the goal that we wanted to. So we have the periodic orbits, and so I can actually just advertise what I'm going to be talking about in the parallel session now. So I'm going to be explaining more about the class of the tentacular class, and to say what kind of things we can still define the homology for. And I'm going to just talk a little bit more about the proofs of the theorem. So if anyone is intrigued by this first part, I very cordially invite you to join me for the proofs and for maybe some discussions. I would also like to hear questions from you, and maybe learn something from you too, hopefully. So, but right now I'm gonna just thank you for your attention, and
thank you very much, Jagna. Thank you. Let's all give Jagna a round of applause, including emojis. Emoji applause, please. Thank you for a wonderful talk.